Hey guys, today we will be getting into confidence intervals. So this is going to be an extension of what we finished in chapter 17 with the sampling distributions. So the kinds of scenarios where you will see this kind of concept being used for confidence intervals is questions like this. So if you think about it, we can never realistically sample all of the United States voter pool about their political alignments. Instead, all we can really do is take a sample out of the voter pool and hope that they're representative of the entire population. Once we get a sample proportion of people that support a certain political party from our sample group, what can we do with that number? So with that number, how can we estimate the true proportions? So let's say we have political party A. So taking a sample of 50 people and questioning them about their political alignments, let's say we found that 30% out of those 50 people are in support of political party A. So using that 30% from our sample, how can we use the 30% to make a prediction about what proportion of the entire United States is in support of political party A? So the way we make estimations about the population proportion from the sample proportion is through confidence intervals. So the purpose of a confidence interval is to take a sample proportion and use it to estimate the exact value of the population proportion. So the actual definition of it is a range of numbers around our sample data that we think the real proportion is inside. So going back to our political party example, if we found that 30% out of our 50 people were in support of party A, we create a range of numbers around the 30%, so maybe it would be 20% to 40%. And we're going to say that we think that the real proportion is inside of there. I won't give you the math for it yet, let's just focus on the concepts. So you can never be 100% certain that your real proportion is inside the range that you constructed, and so there's this thing called confidence levels. The most common way of saying it is I am 95% confident that the true proportion of people in the United States who favor political party A is between X and Y%. So what this means is a little bit complicated. Let's first draw out the sampling distribution for this proportion. So you'll remember that for all proportions, no matter what the original population looks like, as you keep taking samples from it, it will fall into a normal model around our center of P. So it will always center around the true proportion. And as we take samples, maybe we'll get a p hat over here, or a p hat over here, or a p hat over here, where p hat is our sample proportion. Remember, p is the population proportion, p hat is our sample proportion. So what you're doing in your confidence interval is once you get your sample, you're reaching outwards from here, and you're hoping that your p is within those arms. So each of these little dots, each of these data values is going to stretch out its arms, and it's going to hope that their P is in there. Let's say we get a point out here. This is kind of far out, so its arms don't quite reach P. What the percentage confidence means is that if you did the reaching out the arms for every single data point inside this normal model, then 95% of those points, once they reach out their arms, will capture the true proportion P. So that's what 95% confidence means. It basically means that 95% of samples of this size will capture the true proportion of P. I cannot physically express how important this is, that you do not say it as a probability. Never. Your true proportion is always within your range or it's not within your range. It either is or it isn't. So your P has already been set. It's not a random variable that's fluctuating around or anything. It's just sitting there. So it is not a random probability. It cannot be expressed as a probability. You always say something along the lines of, I am whatever % confident that the true proportion is within this interval. If we were instead to change our confidence to 90%, then if we drew out our sample distribution again and we had our P, if we reached out our arms again, because we have a different level of confidence, only 90% of data values will be able to capture P within their arms because we have changed the confidence from 95% to 90%. So for 95% of data values will capture P, 90% 90% of values will capture P. So your confidence always changes how many data points we'll be able to find P. So a quick example, again, I'm not showing you the math just yet. After sampling a few coral reefs in a gulf, we get a proportion of 0.2 coral reefs that are infected with some disease. So 0.2 here means 20% of the coral reefs that we sampled are infected with some disease. This does not say anything about the true proportion out of all coral reefs that are infected with the disease. From there, we calculate a 95% confidence interval that the true proportion of coral reefs is between 0.12 and 0.28, so 12% and 28%. So what does this mean? So the true proportion of all coral reefs that are infected with the disease, we will say is P. We will likely never know what P is, but we do have a 0.2. So the 0.2 is floating around somewhere in this normal distribution. We don't know where it is, but it's somewhere in here. I'm just going to take a wild guess. Let's say it's here. And then we got a 95% confidence interval for it. So that means we stretch out our arms, and then maybe P is in here, maybe it's not. We're not sure. So we had our 0.2 as our P hat here. This point is our P hat. Again, it could be anywhere on the graph. I don't know where it's actually supposed to be in relation to P. This is just a complete guess right now. But let's put our 0.2 over here. And we made a confidence interval from 0.12 to 0.28. One thing you'll notice immediately is that the amount that you stretch out on either side is the same. So we went out 0.08 on this side and 0.08 on this side. So we created an interval and we think that our true proportion is within there. So that is the concept. Here's the math. So our important numbers are our P, so that is the true proportion. This is what we want to find. However, we will not be provided with our P. We will only have our P hat. So that is our sample proportion. Our P hat, that's what we got from going around and performing an actual sample. Two other numbers that you will need is your Z critical and then your standard error. So your Z critical is a sort of reference value that you will always get from the calculator. It's a special number that changes based on how confident you are. So if you have increased confidence, then your Z critical will increase. If you're less confident, then your Z critical will decrease. And then you have a standard error. So your standard error of P hat is equal to the square root of P hat Q hat over N. This should seem very familiar because it's the same standard error that we have for all proportion questions about sampling distributions. And then from your standard error, you can get a number called your margin of error. So your margin of error will be equal to your Z critical times your standard error of P hat. So again, something to keep in mind, and a really easy thing to get confused, is that your P and your P hat are two different values. Your P is always what you're looking for. This is your true proportion, your population proportion. P hat is whatever you're getting from a small subset of the population. Maybe this is representative of the population, maybe it's not. This is just a sample. Your Z critical value can get a little bit confusing, and it is based completely on the percent confidence that you have. So the way you think about it is this. Let's pretend that our P hat is our P. So let's just forget about trying to find a P right now. Let's say that this is our P. So if we went out by 2 standard deviations, so let's say this is 2 standard deviations out this way and 2 standard deviations out this way, then we have captured 95% of data values within these two arms. Because according to the empirical rule, 95% of data values lie within 2 standard deviations of your mean. When you're talking about confidence, if you want to make a 95% confidence interval, then you imagine that you want 95% of data points within your 2 arms. So that means from your P hat, you go out 2 standard deviations. And what you want to look for, your Z critical value, will be this number over here. So this is your P hat plus 2 standard deviations. What it tells you is just how far you're going to go out based on how confident you want to be. So if you want 100% of data values, then your z-critical value or your upper bar for your standard deviations will go outwards this way because you want to capture 100% of the data values within your arms. But if you want to capture 50% of data values, your z-critical will move this way because as you move in your walls, then you will have less data values within your arms and you will narrow it down to 50%. So then your z-critical will again be the value of your upper wall, and it will be this. So it's very difficult to calculate by hand, but there is a calculator function called inverse norm. If you want extra information about it, you can look in my calculator video, but the main point of it is it takes in some area of the normal model, and then it spits back out a z-score. By the way, your mu will always stay 0 and your sigma will always stay 1 for the inverse norm function. So if you put in an area of half, then it'll count up from negative infinity all the way up until it decides that it has reached half of the area of the normal model, and it will give you back the z-score that it's on. So it will give you back 0 if you're on the standard normal model. So how does this relate to our z-critical value? Well, we know that our z-critical value is our upper wall for whatever percent confidence that we're doing. So if we did 97% confidence, then you would have 95% contained within the center, and then you would want to find the value of your upper wall. Or to be more exact, you want the z-score of your upper wall, not the exact value. Conveniently, we know that our inverse norm function does return a z-score, so all we need is to input some area. We need to find some area that'll give us back the z-score that we're looking for. So as we find our z-critical value for 95% confidence, we know that we're moving up from negative infinity to our upper wall, and then we want it to spit back what the value of our upper wall is. That means we need to find the area from negative infinity to our upper wall. Well, we know that we have 95% here, so that's part of our area, but then we also have the part from the lower wall down to negative infinity. So how do we find this? We know that your normal model is perfectly symmetric, and we also know that this area contained within the walls is also perfectly symmetric because we stretched out by 2 standard deviations in each direction, so that makes it the same. And the third thing that we need to focus on is that we have 95% of the graph here. So that leaves 5% of the graph outside of the walls. And because we know that the normal model is perfectly symmetric, that makes 2.5% of the model over here and 2.5% of the model above the upper wall. Now we know that everything from negative infinity up to the lower wall is equal to 2.5%, and then we have 95% from your lower wall to your upper wall, and that is all we need. So adding up these two areas, we get 97.5%. So we would put in an area of 0.975 into the calculator with a mu of 0 and a sigma of 1, and it would give us back our z-score, which is also called our z-critical value. I know it's kind of confusing now because we have two z names. We have a z-score and a z-critical. The difference is that although your z-critical is a z-score, your z-critical is used specifically to make confidence intervals. So if your z-score is being used to make a confidence interval, that makes it a z-critical value. If we instead decided to do 90% confidence, how would we change what we put into the calculator? Well, if we want 90% confidence, that means we want 90% of values within the two walls, and that leaves 10% of the data outside of the walls. Because of symmetry, that's 5% on each side, because 10 divided by 2 is 5. And so putting into the calculator, we need everything from negative infinity to our upper wall. So that's 5% plus 90%. So into the calculator, we would put 0.95, and then we would get our z-score back, our z-critical value. There's two main values that you should memorize, honestly, because they're used so much. The most common confidence levels that you see in confidence intervals questions are 95% confidence and 90% confidence. I'll tell you straight off the bat, the z-critical for 95% confidence is about 1.96, and the z-critical for 90% confidence is 1.645. These are two numbers that you must memorize just to save yourself so much time, rather than having to solve out what the area you need to put into the calculator is and actually going to the calculator and getting your score back. So finally, we have our margin of error. I mentioned this briefly earlier, that's equal to your z-critical times your standard error, but it's basically the amount that you're stretching out on each side with your arms. So you have your p hat as your center, and you're going out by the margin of error in this way, and you're subtracting the margin of error in this way to get the ends of your interval. And the formula for that, again, is over here, and if you want to expand it out further, it is equal to your z-critical times your square root of p hat q hat over n. So that means that our upper part of our interval, the upper wall of our interval, is equal to p hat plus z-critical times the square root of p hat q hat over n. Putting that all together, this is our final formula to get the upper bound and the lower bound of our confidence interval. P hat plus or minus the margin of error. Expanding that out, we know that our margin of error is equal to z-critical times the standard error, and then expanding out further, we know our standard error is equal to the square root of p hat q hat over n. Here's some practice with that. Let's say a science lab samples 104 sea fans from along the Yucatan Peninsula, please forgive my pronunciation, and they find that 54% of them are infected with a disease. Estimate the true proportion of infected sea fans in the area with 95% confidence. So first we need to find all of our important numbers to calculate a confidence interval. Coming up here, this is our formula for it. We need a p hat, clearly. We need a z-critical value, and we need a standard error. And what do we need to calculate a standard error? That is p hat again, q hat, and n. So that's everything down here. So first, what is our p hat? That is our sample proportion. So even though they didn't give us a direct percentage here, we know that 54 out of the 104 sea fans sampled were infected. So putting that into a proportion, we have 54 over 104, which is equal to 0.5192. And then easily we can calculate q from that as well, because q hat is equal to 1 minus p hat. So that is equal to 0.4808. Now we need our n. So again, n is our sample size, that is how many sea fans we sampled. We know that is 104. And finally, we need a z-critical value. There's two ways you could do this. One way is if you already have the z-critical for a 95% confidence interval memorized, that is great. That is 1.96. But if you do want to put this into the calculator, again, you would need an area, and then mu is default as 0 and sigma is default as 1. So what is our area? So we know that we have 95% confidence, and then we have 5% left outside, right? So we add 95% plus 5% divided by 2, which is 2.5%. So we get 0.975. I know that was really rushed, but what you're basically doing is you're adding your confidence level with half of what's left outside, so half of the 5% left outside of your 95%. Now that we have all the numbers that we need, we can plug them into our formula to get our final confidence interval. So we need our p hat, so 0.5192, plus or minus our z-critical value of 1.96, times our standard error. So our standard error of p hat is equal to p hat times q hat, 0.4808, over our n, so our sample size of 104. This is equal to 0.5192 plus or minus, putting everything together for our margin of error, that is 0.09603. And then now we just need to add that to get our interval, and we get 0.4232 as the lower bound of our interval, and 0.6152 as the upper bound of our interval. So how would we conclude? We can't just leave it at this. We would have to say something about how confident we are, as well as what our lower bound and upper bound of our interval ended up being. So the way I would write it is like this. I am 95% confident that the true proportion of infected sea fans along the Yucatan Peninsula is between 42.32% and 61.52%. So we gave our confidence level, our context, and then the lower bound and the upper bound of our interval. So what if we changed how confident we are? How does changing confidence affect the size of our confidence interval? So if we write out the formula for a confidence interval again, we see that it is equal to p hat plus or minus c critical times your standard error. You know that your standard error is equal to your p hat q hat over n. So which of these numbers will change if we change our confidence level? Well, our p hat will always stay the same, and that will make our q hat always stay the same, and our sample size will not change either. The one thing that is affected by how confident we are will be our z critical value. So I mentioned earlier that our z critical value is derived from the normal model. If we have our p hat here, and then we have some level, our x% confidence in the middle, we know that this is our z critical value. So let's pretend that our x% confidence is 95%. So this is our z critical value. Now let's say that we suddenly want to change it to 99% confidence. So we cross out our 95% confidence here, and we put 99% confidence. That means that between these two walls, we now don't want 95% of data points, we want 99% of data points. So that means we need to change where our walls are. If we want 99% of data points, that means we need to expand our walls. So that means, let's say we move out here. So what does that mean for our z critical value? That means our z critical value moved up as well, so it's here now. So one thing that you can notice here is that as we increased our confidence, our z critical also went up. Now that our z critical has gone up, that means we're multiplying a bigger number to the standard error, and that means that we've gotten a larger margin of error. So applying that to how our interval actually looks, if we have a larger margin of error, that means we're reaching out our arms by a larger distance. So that means once we increase our confidence level, then we have also increased the size of our interval. Confidence up, the size of our interval also goes up. If we have less confidence, then what does that mean for the size of our interval? It also goes down. So a common thing you hear a lot is, what's the point of just leaving it at 95% confidence? If we want to be totally confident about something, why can't we just do 100% confidence? So the thing with your confidence level, if you increase your confidence, you know now that the size of your interval will also go up. So as the size of your interval increases, there's a larger range of numbers that your true proportion is estimated to be in, and that means you're also losing the precision of your interval. So you have to find a healthy balance between how confident you are and the precision of your interval. Because if you go too confident, then you will have a way too generalized estimate. For example, I could tell you, you're going to be alive for between 0 and 200 years. That is 100% true. I am 100% confident in what I just said. However, it doesn't help you very much. Like, you know you're going to die before you turn 200, but it doesn't do much to help you as an actual estimate of how long you're going to live realistically. So if you lower your confidence though to about 90%, I could say you're going to live for between 60 and 100 years. That is a little bit more helpful because this is where your average human lifespan is. Again, I don't know where these numbers are coming from. I'm pulling them out of my butt. But most of the time, they won't just give you a really straightforward problem that just says, make a confidence interval, here's the p hat, q hat, and then here's the percent confidence. Other times, they'll have more roundabout questions that have you manipulate the formula more. So we have an example of that here. If we take a sample and find that 70% of people in that group have TikTok, how large was the sample if we got it within 3% accuracy at 96% confidence? So here, we're not making a confidence interval anymore. What we're looking for is how large the sample was. So we're clearly solving for our sample size. So sometimes if you'll look at these, you'll think, I don't really know where to start from. So in these cases, you just sit down and list out all of the numbers that they gave you. So what do I have to work with? First of all, it seems that they gave us a p-hat. They marked that down with the 70% here. So this is an important number, clearly, and it is our p-hat. They also gave us a 96% confidence. What can we do with confidence? So out of all of the numbers in our formula, there is one number that we can solve for with only the confidence level, and that is our z-critical. So clearly it looks like we can get a p-hat, a q-hat, and a z-critical right off the bat, and then we can somehow try to solve for n. So our p-hat is 0.7 for 70%, and from there we can get q-hat too, because we know that p-hat and q-hat are closely related because they add up to 1. So 1 minus 0.7 is 0.3, which is equal to q-hat. Now our n we don't know, so we'll just skip that for now. Now what about our z-critical value? So our z-critical value we can get from our inverse norm function. And what we need is an area, a sigma, and a mu. So mu and sigma we already know is going to be 0 and 1 by default, but what about that area? So we have 96% confidence, and we're going to use that percent confidence to derive our area. So 96% confidence means that 96% of data points are going to be within our two arms again, our two arms centered around the mean. And that leaves 4% outside of those arms. And since we only need 1/2 of what's left outside, so everything from -infinity up to that upper wall, then it's going to be 96%. So we add up 96% plus 2%, which is equal to 98%. So our area is 0.98 with a mu of 0 and a sigma of 1. That is everything we plug into the calculator, and the number we get back out is 2.0537. There's our z-critical value. Now let's see what we can do with these numbers. One final piece of information that they gave us is hidden in the last sentence, within 3% accuracy. What the words within 3% accuracy means is that we got an interval that estimated that our population proportion is within 3% of our sample proportion. To take that further, that means that we stretched out our arms by 3%. And we know that our arms is equal to our margin of error. So our margin of error is equal to 0.3. And what is our margin of error equal to? So we have a nice pretty formula there. It is equal to your z-critical times your standard error. If you want to write that all out into a formula, we have now that 0.03, our margin of error, is equal to our z-critical times our standard error of the square root of p-hat, q-hat over n. So this is perfect because we only have one variable left in the equation. We only have n, and that's what we need to solve for. So solving out this equation to isolate n, we divide by 2.0537 on both sides to get 0.0146 is equal to the square root of, I multiplied our 0.7 and 0.3, so 0.21 over n, and then solving that out, we get that n is equal to 984.126. So our sample was about 984 people. So in order to be able to make an interval in the first place, there are 4 conditions that you need to be able to satisfy. These should look really familiar because we have done this before for our sampling distributions in chapter 17. So first we have our independence condition. Does one CFAN having a disease affect whether another CFAN has a disease? Then we have, is a random sample taken? Did we sample under 10% of the population? And then our success failure condition, aka our large enough condition. So 10 successes and 10 failures. But instead of NP is greater than or equal to 10 and NQ is greater than or equal to 10, that's what we did for our proportions in chapter 17. Because we're working with estimates here, we will do n times p hat and n times q hat instead. So we will go with our sample p and our sample q. So something that you'll get asked a lot is, how do you manipulate these intervals to get what you want? So how would you get a more precise interval? So there's 2 different ways, and you get these all from looking at your formula here. So z-critical times your square root of p hat q hat over n. So if you look at this, you know that your p-hat and your q-hat are already fixed. You can't really do anything to change these anymore. So your p-hat and q-hat are out of the picture. So that means that there's two other variables that you can manipulate in order to get a more precise interval. The first thing is the one that we have already talked about. It's your z-critical. Because you know that if you change your confidence level, then you can change the size of your interval. If you want a smaller interval, that means you want a smaller z-critical, and that also means a smaller confidence level. And that makes sense because if I give a really, really precise estimate about something, I'm not too confident because it's so precise. But if I give you a really broad range of stuff, then I can be really confident about it. Another way is in our n. So this one might not make too much sense logically at first, but if you look at it from a mathematical perspective, if you increase your n, then your denominator over here will get really, really big. If your denominator gets big, then your p-hat q-hat over n gets really small because n is in the denominator. Now that would make the square root of p-hat q-hat over n also a small number, thus making the entire margin of error a smaller number, and therefore giving you a more precise interval. So increasing sample size and decreasing confidence will get you more precise intervals. Sometimes questions will make you construct an interval without actually taking a sample beforehand. So what if I told you to give me an estimate of how many CFANs were infected? Or what if I told you to construct a confidence interval for what percent of people support political party A without taking a sample, without giving you your p-hat and your q-hat? The main way to do this is through a worst case scenario. So if you think about it, everyone wants a precise interval. They want a good estimate. So your worst case scenario will always be maximizing the size of your confidence interval. That's not what you want most of the time, but sometimes you'll be forced to do this. And so you'll have to work with the worst case to give a general idea of what your confidence interval will end up looking like if we actually took a sample. So if we look at our formula yet again, it is p-hat plus or minus z-critical times p-hat q-hat over n. So our z-critical and n, let's say we were already given those, but we don't have our p-hat and our q-hat. So what you'll have to do is maximize the size of your confidence interval to get a general idea of what your scenario is going to look like if you took a real sample. So how do you maximize your margin of error to maximize the size of your interval? So you know that your z-critical and your n, you can pretend that these are already set. So cross them out of the picture. We can cross this one out too because we're only working with the margin of error. That's these terms over here. So how can we manipulate? How can we make up a p-hat and a q-hat to get a bigger margin of error? So what you basically want to do, in simple terms, is get the biggest possible product between p-hat and q-hat. So which two p-hat and q-hat values multiplied together will give you the biggest number? The answer to that is 0.5 and 0.5. A p-hat of 0.5 and a q-hat of 0.5. That multiplied together will get you 0.25, and that is the largest thing that you can get when keeping p-hat and q-hat both under 1. So if questions will ever ask you for a worst case scenario, or they ask you for a confidence interval without actually taking a sample or giving you a p-hat, just do 0.5 and 0.5 as a worst case scenario. So finally, once you have your interval, you need to be able to interpret it. So this sentence you have seen before, I wrote it for the practice question. This is where you give your percent confidence, so 95% confident, for example, that the true proportion of infected CFANs is between X% and Y%. And then you would give the lower bound and upper bound of your interval. So if they ask any further, what does this interval mean? You've given me the proportions that you think the true proportion is between, but what does this 95% confident mean? What does this whole interval stand for? So it means that if we're working with a 95% confidence interval, it means that 95% of repeated samples of this size will yield confidence intervals that capture the true proportion. Going back to our CFAN question, it would mean that 95% of repeated samples of this size will yield confidence intervals that capture the true proportion of infected C fans. So this goes more into the big picture of what these intervals mean. That's it for confidence intervals. Good job, you made it. Yeah, long video, sorry. They will get shorter. I promise you it gets better. Again, this is another big concept. Thanks for listening. Hope you learned something. Peace.